So much, Dr. Kutsia. It's always a pleasure listening to a unique ways of expressing science. Thank you so much. We have our next speaker with us. We have Dr. Arafat from SP College, Srinagar. So kindly go ahead with your talk. He'll be speaking about quantum computers, right? Thank you.
तो कहाँ पे इसमें एंटर करना है? What I have to do?
Right and left.
Okay, thanks. Thank you for giving me an opportunity uh, to be the part of this conference, to be the part of this JNK Science Congress. I think the day was started from Dr. Muzaffar Lone, and he was talking about quantum computers. And even though there were certain things that were going ahead of our heads, so I have a basic talk on quantum computers. If I get some more time, then I can extend this talk to nanotechnology. So uh, these are the contents of my talk, and I'll give you the introduction. Then I'll try to compare the classical computer with quantum computation. Then, if time allows, I'll extend my talk to quantum dots, and I may show some results. I don't think that time will come. So let's start with this photograph. You can see this photograph. What we have is, suppose I have a ball, and I have a ball in my hands, and if I throw this ball on the wall, there's a possibility that this ball will reflect back. If the energy of this ball is less than that of that wall, and if the energy of that ball is greater than that of the wall, then there is a possibility that this ball can be on the other side of the wall. But the classical intuition is that the ball will be on the other side only if it breaks the wall. That's the classical intuition. That's how we live. That's how we perceive things around us. But if I tell you that I have a ball, I shoot this ball on a wall, and the ball appears on the other side of the wall, you will say, "Come on, this is against my intuition. It's magic. It's not the reality." But when we go to the atomic scale, when we go to subatomic scale, when we talk about atoms and molecules, we have a different story. And if this ball is an electron, this electron will cross the wall without breaking it. And this is what's called as quantum mechanical tunneling. And quantum mechanical tunneling, we are as humans, we are as bodies because of quantum mechanical tunneling. If I take an example of nuclear fusion that's taking place in sun, what happens there? You have two protons. And all of us understand that if we have like-charged particles, they will not merge into each other. If we think classically, even though the core of the star is very hot, it has tremendous energy, but that energy is not sufficient to bind the two protons into a nucleus. This is possible only due to quantum mechanical tunneling. So, look at this photograph. There's a man delivering a lecture. His name was Richard Feynman, the most popular theoretical physicist who came up with the theory of quantum field theory. And he has an argument. The argument is that nature is not classical. So whatever we perceive, that's classical. Whatever our intuitions are, that's classical. And if you want to understand the nature, you can understand it only if you are quantum mechanical. If you work out the problems at quantum level. So I will take this talk to the quantum computer because that way I can shorten my talk. There is another important argument given by this man. And what's that argument? He says in American Physical Society in 1959, he comes up with a mathematical argument that there is a plenty of room at the bottom. And this statement of this theoretical physicist becomes the basis of what we have in the form of nanotechnology. And it is this argument that has led different fields of science to come together and work on the field, nanotechnology. And what was the argument? The argument was, why can't we store 24 volumes of Encyclopedia Britannica on the tip of a pen? Why can't we have robots that will go into our bodies? They will move in all our veins, through all vessels, and check out what's going on. This was the argument of this great personality. So look at this photograph. See, this is probably the first mechanical computer. It would have been looking like this. And if you see this photograph closely, what you have the wheels. You have the wheels. And what wheels you have to do with those wheels? You click, you no click. Click, no click. This click and no click was used in World War II. And if you see a person in front of this mechanical computer, there was a man in the midst of World War II when Germans had built a code, and that code is called Enigma code. His name was Alan Turing. He was a mathematician. He was a scientist. And it was this person who broke the code of Germans. It was called as Enigma code. And people say that if he would not have broken the code, the World War would have extended for more 2 to 3 years. Now, I don't want to go into the history of this argument. I'm trying to tell you that you have a machine, and this machine has only 2 states. It has a click state, it has no click state. Now, look at this photograph. What you have laptops, your tablets, your mobile phones. They are all working on the same principle. Click, no click. There's no difference at all. They are working on the Newtonian mechanics, a mechanics that's completely predictable. You can predict everything about the ball. If I have a ball in my hand, you threw this ball, you can tell about this ball. What will be its speed at some point of time? With what force that ball will fall off the ground. So all of these things that you are seeing in this photograph, they are not anything more than that of those clicks and no clicks. Yes, no, right, wrong, 1, 0. Classical computers. So these computers that we have, that we are working with, Whether you have supercomputer or you have 1,000 of supercomputers, they are all working on the same principle. Click, no click. Click, no click. And classical computers, they work in the same manner as the Newtonian mechanics works. Newtonian mechanics is deterministic, as I was telling you. You have a cause, you have an effect. Classical computers, predictable, deterministic. You have a cause, you have an effect. So classical computers, even the supercomputer that you're talking about, that's a classical computer because it works on the same action. The photograph that I showed you in the beginning, the same action, click and no click. So they are all governed by Newtonian mechanics. You have the basic things of a classical computer. You have hardware, you have transistors. These transistors are doing the same job. Yes, no, right, wrong, 1, 0. And then you make the logic gates out of these transistors. You translate these gates into a processor. You write down algorithms. Then you put some syntax on these algorithms. And you come up with programs. And what you are doing finally, you are giving an input, and that input has an accurately known, accurately predictable output. Now look at this photograph. In the left side of this photograph, you have a computer with 250 transistors. On the right side of this photograph, you have a mobile phone having 19 billion transistors in it. Is there any difference in the mechanism of working between the two devices? The answer is no. The way the transistors that are working in a computer with 250 transistors is same as that of the transistors, as that of the mobile phone having 19 billion transistors. And what is another important point here, that you have these 19 billion transistors, every transistor is working independently. One transistor cannot influence another transistor. Every transistor is doing its own job. They are working same way, click and no click. There's no difference. Maybe the difference is the mechanism of achieving those things, but they are the same things. So there is no entanglement. I'll say these 19 billion transistors are working independently. I'm trying to prove the point. Now let's talk about the quantum computer. You can build a quantum computer based on these three arguments. And I want to pass the idea. These three arguments are quantum superposition, quantum entanglement, and interference. Now look at this photograph. I wanted to move, but I don't have a way to move here. Look at this photograph. What you see, you have a wall. This wall has two holes. And behind this wall, you have some screen. I have a gun in my hand. This gun can shoot bullets. I'm using my gun. I shoot the bullets. Now, what's going to happen? Some of the bullets may come back. Some of the bullets may reflect in some other direction. And some of the bullets will pass. And what do you expect on the screen that's behind this wall? You expect that these two regions that you can see those two regions, these two regions will be affected. So what was it that I was shooting on this experiment? I was shooting particles. You say I was shooting particles. That's why you could hit those two regions on the screen. Getting my point? Fine. Now, the next argument. I'm using the same kind of experiment, but now I'm using light. And when I use light, the light is allowed to pass through these slits, and what I obtain on the screen is fringes. I obtain something bright. It's coming on the top. Then dark, then bright, then dark, then bright, then dark. It goes like this. Now I want to explain why my screen is like that. I can explain the screen only when I will say, come on, light must be a wave. Only then you will have the interference pattern on the screen. It's much like water waves. If you have stones, you allow them to fall in the water, you will have water waves. And in water waves, what you will have? You will have humps, you will have depressions. You will have humps, you will have depressions. Your hump is a bright line, and your depression is a dark line. And this bright line is called constructive interference. We say that the amplitude is maximum because of constructive interference, and the amplitude is minimum because of destructive interference. Is this clear? I think I'm able to cross the message. Now, this is my target. This is my target. I want you to focus on this photograph. In the first case, I had a gun with bullets. In the second case, I had a wave. Now, in the third case, I have a gun, but this gun shoots electrons. Look at me. Now, I have a gun, I'm shooting electrons on this double slit. Electrons are particles, right? And when I shoot the bullets, when I shoot these electrons, what am I seeing on the screen? I'm seeing an interference pattern. What does that mean? That means electron is not a particle. It is a wave. Now I'm going to tell you another important thing. But now I want to know to which slit which electron has gone. This is the important argument that you'll not find in books. Now you have those two slits. In front of those slits, I will keep a detector. I will keep a detector. This detector will tell me that which electron is gone through which slit. Has it gone through slit 1 or has it gone through slit 2? Come on, come on. Now, when I keep the detector, I'm not able to see the pattern. I see the same photograph as I showed you, when I was talking about the bullets. There is no fringe pattern. You have the two lines on the screen. So electron is small. Something wrong is happening. When I'm trying to see the electron, which way the electron is coming, I am confused. What's going on? It's showing me out. And when I don't look, I don't use the detector, it's telling me I'm not a particle. I'm someone who is everywhere on your screen. So what's going on? I should go back. Now I am shooting one electron in 1 second. I'm shooting one electron in 1 second. What will your human intuition tell? It will tell you the electron will go through slit 1 or the electron will go through slit 2. I use the detector. When I use the detector, the electron goes either through the slit 1, it hits the screen, or it goes through the slit 2. But when I take off the detector, I find the patterns. When I'm not looking at this one electron, it is telling me, oh, I'm a particle. But when I'm taking this detector away, it is telling me some other story. What's that? That is, this electron, how can I explain this thing? How? How can I explain this fringe pattern on the screen? I can explain this fringe pattern on the screen if I say, come on, this one electron is passing through both the slits at one point of time. Now your slit 1 is 0. Your slit 2 is 1. This is called qubit. This is called quantum bit. Your electron is making an action at 2 points at same point of time. Getting the point? I think I'm able to cross the message. So it's much like this man. This man is in superposition. It is the reality. It's not wrong when you go to the atomic and molecular level. This person is at two places at same point of time. This is called quantum superposition. And this quantum superposition is exploited in a quantum computer. And it makes a quantum computer. It becomes the basis of a quantum computer. Now, you can see this man on this photograph. This man is Erwin Schrödinger. And in the right side of this man is the Schrödinger's equation. I will not tell you anything about this equation. I don't want to confuse you. But I hope everybody has heard about the Schrödinger's cat. You have Schrödinger's cat. Now, what this Schrödinger's cat is, there's a box. There's a box. You have a cat. You will put the cat in the box. You will close the box. Now, what about the cat? The cat can be in many states. The cat can be dancing. The cat can be jumping. The cat can be sleeping. The cat can be alive. The cat can be dead. But the moment I will open the box, I will find only one state of the cat. The cat is just an example because cat is a classical object. This cat is your electron. So when you are not looking into the box, the electron was in multiple states at the same point of time. But the moment you open the box, this is called the collapse of the wave function. The moment you open the box, you find the cat in just one state. Another example is there. You can have a ball inside the box, you can have the ball outside the box, but in quantum superposition, the ball can be outside the box, inside the box at the same point of time. Now, this was the argument, this was the question raised. What is quantum entanglement? Now, quantum entanglement is a reality. I would like to start with that, with this argument. If you have two particles, then I would like to conclude it. If you have any questions, you can ask. Okay, that's beautiful. Now see, if we have two particles and there is some kind of interaction between the two particles, they are entangled. If they are entangled, if this observable universe has a North Pole and a South Pole, you have the two particles. These two particles are entangled. You separate them, put one particle on the North Pole of the observable universe, put another particle on the South Pole of the observable universe. And if I make a measurement, the point is, if I make a measurement on the particle that's on the north side of the universe, there will be an instantaneous reaction to that measurement with respect to the particle that's on the other side of the universe. Think about a man who is the greatest mathematician of all time, a person who came up with general theory of relativity. I fail to understand it at times. He is the man coming up with a paper. That paper is called EPR. And that paper tries to disprove this entanglement. How is it possible that you can have instantaneous transformation of information from one particle to another particle, even if the two particles are at infinity with respect to each other? Albert Einstein wrote down a paper. This is called EPR, Einstein, Podolsky, and Roseman. And in this paper, they used what I started with, human perception, human intuition. They used all those arguments to say that Bell's inequality is right. But you can see people are having Nobel Prizes in entanglement. So people having Nobel Prizes in entanglement is a proof that entanglement is a reality. The point that I was telling you, that if you have a particle at North Pole of the universe, you make a measurement on that, the particle at the South Pole of the observable universe will react to that measurement. So I'll stop here. Any questions? Thank you, sir. You missed me in your list, yeah. What are you talking? I'm not in the list. Thank you, sir. Thank you. Thank you, sir.
Thank you so much, sir. We mean every word that Dr. Tauseef spoke.